All right, well, thank you all for having me. I actually grew up coming to these. I started watching Steve and Kachun and many other space scientists since I was 14 and a volunteer and trying to figure out what the heck space science was. It was really exciting. So I'm so excited to be up here with you guys for the first time. But one of the stories that really excited me this month was looking at our own galaxy with the Milky Way. I've been an avid stargazer for a long time, and I've seen views like this when I'm lucky enough to get out under the night sky and wondered, how the heck do we determine the shape of our own galaxy? And the analogy that I think is really appropriate that the authors of this paper that came out this month use is, it's like standing in the middle of Sydney Garden trying to figure out the shape of Australia. And so we see a lot of great scientific illustrations like this that are based on our understanding of our galaxy, being able to look at the stars that we can see and plot their positions. And we know it's a barred spiral galaxy, and typically we see this view from head on where we have those beautiful spiral arms. But when we look at it edge on, most of the time we see depictions like this. I used to say it's flat like a CD, but I'm learning kids don't know what CDs are anymore. And that's making me feel old. So we'll go with pancake. It's flat like a pancake is how we most of the time see our depictions of our galaxy. And one of the things that this depiction really shows us is how hard it is to be able to determine what our galaxy looks like from within, because you can see we've got a lot of dust and gas that obscures our view. So that was why I was really excited this month when a new paper came out that determined this is not the shape of our galaxy, that we actually have a really warped shape. So how were they able to do that? So first of all, they took a lot of data from all sky surveys that were done in visible light, but to be able to peer through all of this dust, they used an infrared space telescope called WISE. It's an older telescope that was launched in 2009. They went through its catalog and were able to find several what we call Cepheid variable stars, and they could see those through the dust thanks to this infrared telescope. So what is a Cepheid variable star? How many of you have heard of those before? Okay, so a handful. So Cepheid variable stars are one of what we call a standard candle. They're one of the ways we measure distances. And these are really bright, huge, giant stars that live fast, die young. They are typically yellow in color, and towards the end of their life, they get a bit of an instability in them that causes them to pulsate. So they both expand in size and change temperature, and they do this very regularly. And how frequently they actually vary in brightness and go from peak to peak has a direct correlation with how bright they are. So we can measure the distance to Cepheid variable stars that are close by using an independent method of measuring distance and find out exactly how bright they are. And so they were able to come up with this period luminosity relationship. And this was an amazing female astronomer from 1908, Henrietta Leavitt, that did this. And so we were able to find, these scientists from China and Australia, were able to use a catalog of 1,399 Cepheid variable stars. And they took this period luminosity relationship and they said, oh, okay, well, if it has a period of so many days, it should be so bright at its source. But oh, we see it a little bit dimmer. That means it's a certain distance away. We can do that with 1 over distance squared. One of the easy things we can do in astronomy. Whew. All right, so they were taking these catalogs and they were able to create a map of our galaxy. So this is what they created. I wanted to keep it still for just a second to show you this little triangle here is our sun. And what they did is they plotted that distance. Let's see if this will play now. In all 3 dimensions. So you'll see our axes here are X, Y, and Z, and it's labeled in kiloparsecs. Kiloparsecs is a unit of distance. A parsec is 3.26 light years. And so you'll see that they have a lot of stars that are measured distances on our side of the Milky Way because those are easy to see. But they were also able to measure some on the opposite side. And they found something really interesting. Our galaxy is kind of S-shaped. It's warped and twisted. Now, this isn't unusual in our universe. We see dozens, at least, of other galaxies that have a warp to them. And we've known since the 1950s that hydrogen gas was able to have kind of a warp shape on the outside of our galaxy, but we were never able to measure it with stars and see if stars followed that gas. And so this was the first time they were able to do that. And they plotted those together, created a nice kind of model of what they think our galaxy would look like. Again, there's our sun there. And so the picture they put together looks a little bit more like this. This is a bit exaggerated, but you can see we've got warping going up on one side and down on another side. And their measurements extended out to 65,000 light years from the center of the galaxy. For reference, we're about 25,000 light years. So they were able to measure pretty far out. So the goal of this paper really wasn't to say why this was happening. In fact, all they thought they were going to be doing is mapping the spiral arms. They didn't expect to find this warping and this torque, or this distortion. And so they said, well, why could it be happening? And one thought is torque. That as stars go on their orbits that take millions of years to go around the center of our galaxy, those stars kind of in the inner region of the Milky Way drag along material from the outer edges of the Milky Way, and it kind of spins it up and creates this distorted spiral shape, resulting in this S-curve. So we have a bit of a new picture of our own Milky Way, which I thought was just really neat and interesting. And with that, I will turn it over to Steve, or Kachun, sorry.